Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to apply that very powerful tool we've been using, the substitution method, to our integrals to see how it helps us when we're working with things like reversing the chain rule. So here we have our U substitution definition, and it looks a little complicated, but that's okay because what it really is doing is just trying to basically work you through the idea of the chain rule backward with an integral. And you'll notice that when we look right here, this is effectively the output of the chain rule. And it's simply saying that when you see something that looks kind of like the output of the chain rule, you can use U substitution to simplify it so that you can then take the integral, and then after you've done that, you can put that substitution back and you're good to go. As long as when you do this substitution, your function has to be continuous on the range of whatever your internal function was here. But that's kind of the situation you're getting when you're doing your integral anyway. Now, the easiest way to see how this works is just to look at some examples and to practice with it so that you can tell when it's going to be applicable. The easiest examples for when this is applicable is when you have situations where you have a variable with 1 degree difference. Because when we go to set this up, we're going to be using implicit differentiation. So to do this, we notice, like for example here, we have an x to the fourth and an x to the third. And this x to the fourth is locked inside cosine. Now, if we had a plus here, we wouldn't need to really use U substitution potentially because we could just do normal differentiation here. But in this situation, because these are multiplied, we don't really have any rules that help us with this. So this is a perfect candidate for U substitution because if we substitute x to the fourth plus 2 for u, and then do implicit differentiation, we notice that we get the 4x cubed dx. Well, dx is here, 4x cubed is here. So this du will completely eat those up. So when we do our replacement, x to the fourth plus 2 would go here for the u, and then the du takes away those, leaving us with this really, really simple integral. So we integrate, we get sine u, and then we simply replace the u back with what u is, and boom, we have our answer. Now, on the next example, it's still not super difficult, but it is a little more difficult because we don't have just everything laid out. In this one, we have to do a little bit more work because we still notice that we have the situation we're looking for. We have an x squared and we have an x. But when we do our implicit differentiation, we end up with du equals negative 8x. So we need to get rid of this negative 8. But that's fine because remember, what we're doing is we are trying to get our integral to be in terms of u and du. We want to get rid of all of the x's and dx's, which is fine because we could just move that 8 over as a negative 1/8. So when we do that, all that's going to say is that the x dx is going to be replaced with the 1/8 du, which is fine. So when we do our replacement, we get 1 over the square root of u times, and then we replace the x dx with the negative 1/8 du, bring out the constant term, and do our integral, which again, not a complicated integral because of the substitution. Replace back with the u, and boom, we have our answer. Now, there's an additional thing you can do with this that when I was going through this was called back substitution, and I'll show you what that looks like next. So both of these problems are perfect candidates for U substitution, though it may not look like it initially because they don't fit the situation we talked about in the previous example. If you'd like to try it on your own, go ahead and pause the video, but I'll show you how it works in 3, 2, 1. And so here we have it, that back substitution method I was talking about. And the way that we know we're going to be using this generally is whenever we have a situation where our implicit differentiation isn't going to be getting rid of one of our x's or one of our whatever the thing is we're dealing with. And so in this kind of a situation, what we do, and the reason why I think my teachers called it back substitution, is because we have the u, but then what we do is we just solve back for x and then replace using that more complicated version. So here we just have the u and we replace x minus 1 with u, but then we solve for x and replace the x with this. Now, that doesn't really matter that much, hopefully, when we're solving everything, because our goal here is to get rid of the x, because the x is in a position where it's causing us issues. And if things work out, we'll be able to solve it in a way where it will simplify our integral. And in this situation, it does, because it allows us to take this and convert it into an addition problem instead, so we can then use our integral properties. And as you can see, we're able to solve this. Now, it may not be very pretty looking, but it's at least doable. And then, of course, we substitute back in our u, and we get a rather complicated looking solution, but like I said, it was doable. Now, this part down here is simply the algebra bit you'll have to do afterward. Be careful, because as I said a few videos ago, oftentimes in these kind of calculus situations, the algebra will be the thing that is your downfall. So make sure you're very careful with your notation while you're working through this. And you'll notice over here, I didn't work all the way through. Mostly that's because I was running out of space, and because this is about doing the substitution portion as the example, and not how much algebra can we do, okay? Now, on this example, you'll notice that we actually had to use both of the previous techniques, and it wasn't immediately obvious. So this is one of those situations where you might want to do a little bit of algebra to your integral beforehand. But be careful how much you do, so that you don't do more work than you need to before you do your substitution. So in this example, it was helpful to notice, well, I can replace this whole 1 plus x squared, and then when I do my back substitution, I can replace the x squared with u minus 1. And so the way that's helpful is that when I do my implicit differentiation, I'll get rid of this x dx, right? And then here, the du, I did need to replace it with a du over 1/2. But again, that's not that big of a deal, because everything is getting replaced with u du. I'm not being left with multiple variables in here, okay? And then this x to the fourth, well, that's just x squared squared. So that means, awesome, I've got this, and we know how to handle this. This just becomes a polynomial, which again lets me turn this multiplication that I can't really handle with this method into an addition problem that I can use all of my normal integral properties with. And while it might become messy, it's at least doable. So the last thing we're going to look at is, how can we use this with our definite integrals? Because it turns out that, you know, just like we can take our indefinite integral and then use that for our definite integral, you might then look at this and go, well, great, I'm going to have to get to this and then plug my numbers in. It turns out that we don't even have to actually go back to this point with the definite integral. We can actually just take this and modify the whole thing. I'll show you how. So here's the rule for doing U substitution with a definite integral, and here's kind of the proof of it, or really, I guess you can say a demonstration of why it works, as well as why you have to be careful to check that your function is continuous on the range of that U equaling gx. So literally all you do is exactly the same thing that we were doing with our indefinite integral, but the advantage here is that when you find that u, take your a and your b and then plug them into the u equals whatever your x is. So plug the a in for x, plug the b in for x, and that will give you your new interval. And then what you want to do is, when you construct your substituted integral, do the exact same check that we did before with a definite integral and make sure that this function exists on this interval continuously. And as long as it does, you're good to go. So next up, I'm going to give a couple of exercises for you to practice with, and then of course, the outro. So I hope that overview of the substitution method with integrals was helpful. If you have any questions, feel free to drop into the comments below or join us on Discord. And as usual, the answers to the exercises will be after the outro.